Hello everyone and welcome to this video on frequency modulation or FM. In this video we'll see how to implement frequency modulation and frequency demodulation using MATLAB, and we will investigate a real FM broadcast signal. So let's get started. So the tutorial is structured as follows. First, introduction, then we'll see the FM modulation and demodulation, then we'll see a MATLAB implementation to simulate the frequency modulation and demodulation. Then we'll investigate a real FM broadcast signal. And finally, the conclusion. Introduction. This is Armstrong, and he is one of the pioneers of frequency modulation. He introduced FM as an alternative to the AM or amplitude modulation, which suffer a severe interference and noise problem. So if you're interested in the history of FM, you should read the biography of this man. What is frequency modulation? Modulation in general is the operation of putting information on top of the carrier signal, and frequency modulation is simply putting the information signal or the input signal on the frequency of the carrier. So as we can see here, this is the input signal, an example of input signal, and this is the modulated carrier. And we notice that we have, when the input signal is maximum, we have the higher frequency, and when the input signal is minimum, we have lower frequency. And this is simply the idea of frequency modulation. This is the equation of FM modulated signal. We will not go into the math, but we will highlight an important parameters. So for example, we have the amplitude of the carrier, we have the carrier frequency, and here we have the input signal, and it's modulated in the carrier frequency. We have an important parameter in frequency modulation, which is called the modulation index, and it's defined as the maximum frequency deviation over the maximum input frequency. The frequency deviation or the maximum frequency deviation is defined as follows. We have the parameter k and the maximum of the input signal. And if we have a special case when the input signal is a pure sinusoid, the modulation index will be as follows. The maximum input frequency will be the frequency of the input or frequency of the sinusoid, and the maximum frequency deviation will simply be k, the parameter k, times the amplitude of the input signal. How we can implement frequency modulation? Frequency modulation can be implemented simply using a voltage controlled oscillator, VCO. This block operates simply by changing the frequency of the output signal depending on the amplitude of the input signal, and it's simply the frequency modulation operation. In this block, we can define the carrier frequency FC and the parameter k, and if we give it an input signal, we will get at the output a frequency modulated signal. The demodulation operation can be done by first multiplying by complex sinusoid to translate the FM signal to baseband. Then we take the low pass filter to filter any higher frequency components. Then we will have the complex baseband signal that has the information in the phase. So we can extract the information by simply differentiating the phase. So we can get the final output signal that is proportional to the input information signal. So the FM demodulation can be done using this discriminator circuit, and it's shown here. This circuit will take a complex input and will give us the differentiation of the phase in the output, which is what we want to demodulate the FM signal. So let's see the MATLAB implementation that simulates the frequency modulation and frequency demodulation. So now we'll see the frequency modulation and demodulation simulation using Simulink. Here we have the frequency modulation operation. So this is the transmitter. And here we have the frequency demodulation. And this can be considered the receiver. So in the transmitter, we have a sinusoidal input that goes to voltage controlled oscillator, which simply performs the frequency modulation. The sinusoidal input has amplitude 1 and a frequency of 400 Hz. The voltage controlled oscillator, here we set the carrier frequency to 15 kHz, and this is the K parameter, which is set to 800. So we have a modulation index. This is 1, this is 400, and this is 800. So we have a modulation index of 2. So can be considered the wireless channel. And here we have the receiver, the frequency demodulation operation. First, we multiply by a complex sinusoid of 15 kHz to translate the required band to baseband. After multiplication, we have low pass filter to filter any high frequency components. Then we have simply the frequency demodulation, and here we can see the output signal after a low pass filtering. The frequency demodulation, as mentioned in the presentation, is very simple discriminator circuit. This circuit simply differentiate the phase of the complex signal inputs and extract it in the output. So this is a delay, this is complex conjugate, and multiplied by the complex inputs, and then this take the angle of the signal. So simply this circuit differentiate the phase of the input signal, the complex input signal, and send it to the output. So this simply simulates the frequency modulation and demodulation. And we have an important parameter, which is the modulation index, and in which it is control the bandwidth of the signal, the bandwidth of the frequency modulated signal. So we will see its effects shortly. First, let's run the simulation. Let's set it to 5 seconds. Here we can see various signals. This is the input signal, which is simply a 400 tone. So simply we have an impulse at 400 Hz. This is the frequency modulated signal in time domain. This is the frequency modulated signal in frequency domain. We notice that we have here the carrier, which is 15 kHz, and we have the signal centered around the carrier. So this is after multiplication by complex sinusoid, which translate the signal from 15 kHz to baseband to 0 Hz. And here we have the transmitted signal, the input signal, and here we have the received signal after demodulation. And this is the frequency of the received signal. So we notice we also have our transmitted tone. So to see the effect of the modulation index, so the value of the modulation index control directly the bandwidth of the frequency modulated signal. And to see its effects, we have the frequency modulation page from Wikipedia, and we can see that the value of the modulation index control how many sideband we have in the frequency modulated signal. So we notice that at this specific value, we don't have any carrier, we have just sidebands. So let's test this. So we have this value is 1, this value is 400. What value we should have for k to satisfy the condition? So let's open the calculator. Time 400. So we should have this value. So now we should have a modulation index that suppresses the carrier, and let's see if this is the condition. So as expected, we notice now that we have only sidebands and we don't have any carrier. So the modulation index is a very important parameter, and it directly relates to the bandwidth of the frequency modulated signal, and its effect can be seen for example, from Wikipedia. So this is the effect of the modulation index with the number of sidebands of the frequency modulated signal, and you can test other conditions by yourself. So let's now investigate a real FM broadcast signal. These signals are around us and almost everywhere, and it's extensively used for broadcasting. So this is the FM demodulation implementation to demodulate the FM broadcast signal. So we have various parts. First, this is the complex baseband of the FM modulated signal. We multiply it by a complex sinusoid, so we can tune the demodulator to a specific channel. We have down conversions, so the input signal have a sampling frequency of 4 megahertz, so we down convert it to 240 kilohertz, which is fair enough to demodulate a 100 kilohertz bandwidth of frequency modulated signal. So here we have the frequency demodulation. This should be familiar. We used it in the simulation part. It's simply a discriminator that differentiate and extract the information from the phase of the complex signal. So we have a frequency that has a sampling frequency of 240 kilohertz. To make it suitable for audio device, we down convert it to 48 kilohertz and give it to the audio to listen to the signal. So let's see how we can get the recorded baseband signal. So here we should give it the recorded baseband file, and I downloaded it from here. So this is a recording of broadcast FM signal that has multiple channels, and I will provide you with the link. There is other signals also, but we're interested in the FM broadcasts. And it's basically extracting the first channel and the second channel and convert it to a complex baseband. So this is the receiver, and let's run the code and see the spectrum and the signal and listen to the demodulated signal. So this is the spectrum of the recorded baseband. So we have multiple channels, but now we are tuning to this specific channel. But we can see that we have many other channels. You can tune the demodulator for any of those other channels. This is the spectrum after FM demodulation, and this is the time domain of the final output signal. Here we can see something interesting. We don't have only the audio, which is at baseband. So we notice that we have this tone, and it's at specifically 19 kilohertz. We have this other signal and this other signals. So in reality, the FM modulated signal has not just the mono or the audio at baseband, but other signals. So this is the Nightingale Hertz tone. This is amplitude modulated signal. It's specifically amplitude modulation double sideband suppressed carrier signal. And this is digitally modulated signal. This is binary BSK signal. And to see this signal, let's see the Wikipedia page. So this is the FM broadcasting page, and we can see this is the what contained in FM broadcast. So at first, this is the mono audio, which is what we have listened to, and this is the pilot that we have seen, and this is the double sideband suppressed carrier signal, amplitude modulated signal, and this is called RDS or RBDS signal. So this left and right mean the left or right channel of the stereo or left or right speaker. So we can just listen to a mono audio, or we can demodulate this other signal and extract the left and the right channels and listen to stereo. And this other signal, if you see the channel name on your FM radio, or you see the program name, or maybe you can see the time. So this information was extracted from this signal. So this signal transmits digital modulation, which is binary BSK that contain various information. So you can change the frequency to tune your receiver to any other channel. So in conclusion, we first saw what we mean by frequency modulation and how to implement the modulation and demodulation operations. Then we saw how to simulate frequency modulation and demodulation using Simulink. And finally, we investigated a real FM broadcast signal and saw its properties.